Okay, so let me start by recapping a few things from last class. The first thing, to satisfy Daniel Harlow, I should mention, and probably all of you, the name of what I've been discussing. It goes under the name of Tomita Takasaki theory, and it's in the context of von Neumann algebras. So this object that I defined yesterday is a von Neumann algebra. Okay, so the point, I think the main point is that this is kind of the structure, or an interesting structure that kind of replaces entanglement entropy and quantum field theory if you want to just take the continuum limit and work in the continuum. So, I think it's important to understand this structure as much as we can. So it allows you to define various things in the continuum. Of course, it doesn't allow you to define entanglement entropy because that's somehow infinite. But the basic equation that I wrote down yesterday is sort of a problem. So it's basically, I have some algebra of operators. They're acting on some state in the Hilbert space. This state is sort of fixed and it's special. There's some operator that takes OA acting on this state to OA dagger acting on this state. Okay, and so with some conditions, this is sufficient to specify both of these operators, because then you say that this is an anti-unitary operator. Okay, and so now I've specified, okay, this is some very abstract language, but I have specified this operator. So this operator is then related to maybe some slightly more familiar things. If I write it like this, e to the minus 2 pi k hat, and then k hat was this full modular Hamiltonian, which was somehow a combination of the modular Hamiltonian of the region minus the modular Hamiltonian of the complement region. And it was this combination that we had some idea should be finite because divergences sort of cancel between these two. Yeah. Yeah, let me say that in a second. So Nima's asking about the conditions under which you can solve this, and I will say that. So. Okay. Okay. So yeah. So we can solve. I was going to say that now. Can solve this guy under two conditions. The first is that it's separating, which means that the state is separating for the algebra, which means that this none of the operators annihilate the state. So if one of the operators annihilated this state, then obviously it would be hard to solve this equation. And cyclic is the statement that OA psi is dense in the total Hilbert space. So that means you can create sort of any state in the total Hilbert space basically as a limit, right? So if you take a limit of operators acting on psi, then you can get any state in the Hilbert space. And then, and it's important for some intuition that these concepts are also defined in a finite, tensor product case where you just have density matrices and so forth. And then this condition is just equivalent to rho A being full rank. Right, so it's invertible. The density matrix is invertible. Right. Okay. And then the other thing. So this is just a reminder. This is also a reminder. The intuition behind this equation comes from the local case where we have some Rindler cut. So we have A. Let me write it a bit bigger. So we have A complement. We have some Rindler wedge. And we have two ways to get from over here to over here. One way is to rotate in Euclidean. So this is kind of coming out of the board by amount pi. And then the other way is to reflect using this J operation, which is then just CPT. Okay, and so the pi rotation is just e to the pi ka hat, which is then just delta to the 1/2 using those conventions, so that's that. So you're just doing the two operations, you get back to yourself up to this conjugation. Okay. Good, and the consequences, the important consequences to keep in mind are that, so you know, this J operation takes you from an operator in the algebra to an operator in the commutant, okay? And this operation, which is called modular flow, which we'll study a lot more, this takes you from an operator in A to another operator in A, acting in A, okay? So this is called modular flow. And of course, in the local case, this is just a boost. Okay, so if I boost about the so this is just this boost operation. Okay. All right. So these two conditions, when do they apply? Okay. Stay there. When do these apply? There's a few situations that are known, that are proved. So basically, the Bisignano-Wichmann theorem, which is basically pertaining to this situation, to this local situation, guarantees that quantum field theory in Rindler space with psi being the vacuum satisfies these conditions. More generally, this Rieschleider theorem tells you that it actually applies to the vacuum reduced to any causal region, to whatever causal region you like. These arguments also actually apply to any finite energy excitation of the vacuum. Right. So these are kinds of the states that we might be interested in quantum field theory, and so they're the states where this applies. And you know, so okay. So roughly speaking, this is the formal mathematical way of saying that these states are highly entangled. But they're not, it's important to remember they're not sort of highly entangled in, maybe if you're talking to a condensed matter person, what they mean by highly entangled, which is some kind of volume law. This is just, the area law divergence is enough to give you this, okay? All right. Okay, so are there any questions on this? Yes?
Can you just clarify what you meant by you can solve that? What are you solving for?
That operator, J and the two operators.
J and delta.
Yeah. And basically, because this is an anti-unitary operator, J is an anti-unitary operator, you can just sort of uniquely decompose the combination of them into J times delta. Yeah. Yeah. Okay, so good. All right, so now let's talk a little bit more about modular flow and the KMS condition. Okay, so this is sort of another nice way of expressing the fact that these states are highly entangled. Okay, so firstly, let me define an operation where I take an operator and I flow it by an amount S. Okay, so, right, so firstly, yeah.
By highly entangled, you don't mean the area law. Like, do you mean the moment entanglement, or you mean?
No, I mean the area law, right? So no, it's not. Yeah, that's what it doesn't need to be a volume law. Definitely not.
No, I don't mean the volume law. Just say if I
Whew. Does that make sense? I don't know if that makes sense.
Actually, we have long-range entanglement. This is not volume, right? It's constant. There's some kind of constant of operator there.
I think you still have long-range entanglement, right?
Yeah. I'm just saying, is those things responsible for that, or is it the area?
Yeah. Let me. Okay, the question, I should actually state the question for everyone. So the question is, what conditions under what conditions is this true? Is it just sufficient to have an area law, or do you need some extra long-range entanglement? And I don't actually know the answer, so let me. Okay. Thank you, Aaron, but I'm not going to repeat that, sorry. That was a very long answer, but it won't be recorded, so everyone in the room got it. Yes, question?
Should I think of the J times delta 1/2 as some sort of polar decomposition?
Yes. Yeah, that's right. Okay. All right, so let's define this operation where you can, you can think of decomposing. This is a little schematic, and I probably shouldn't do this, but you decompose the modular Hamiltonian in this form, and then modular flow on an operator in the A region is just acting with the modular Hamiltonian for the A guy. And so the question is, what happens when I complexify S? And so let me define a function where we can study this. Which is two operators in the region A with modular flow acting here. And let me go through this once more because I think I was a bit quick last time. This is sort of a fancy way of writing modular flow. We can use the tricks that Ka, this guy leaves the state invariant, right, which is the statement that it's sort of boost invariant, and just add this for free. And then under this decomposition, because the operator in A commutes with the complement modular Hamiltonian, you can just cancel that out of this thing. And then this just becomes the non-full modular Hamiltonian. So I'm really making a distinction between the hat and the non-hat. And so this is just OA of S, as I've defined it. Okay. Now, one thing we can do is we can bound this function. We can give a bound, f of s, because I can rewrite it as an inner product on two states, one which is the state that I get with acting with this operator and one with this operator. But now I can act with modular flow on both of the operators. So I can rewrite it like this. So I'm actually working from this expression here. S star, this is the complex conjugate. A. And then I can bound this by Cauchy-Schwarz as the norm of these two states. Okay? So the products of the norms of these two states minus, and what you get is the imaginary part of S, 2 times also the imaginary part. So notice what I've done is I've sort of put modular flow, half of it on this guy and half on this guy. And so when I bound, I get something that looks like this. And good. So now we can use the fact that the operator is defined. I think I erased it when the imaginary part of S. This thing is defined as long as this is up to pi, right? Because then that was delta to the 1/2, and so that roughly speaking means that this function is bounded as long as the imaginary part of S is between 0 and the imaginary part of S over 2 and pi. Okay, so that means that this function can be continued into the strip, and some more sophisticated arguments tell you that it's an analytic function in the strip. So analytic. So this strip is, well, let me write it a bit more. Write it bigger. Okay, so this is the imaginary part of S, and this is the real part of S. And this goes from 0 to 2 pi, as this suggests. And so this function is sort of analytic in here, f of s. On the boundaries, well, typically you can have branch cuts on the boundaries, so you could have something like this. Yes. It's just an operator in the region. Any bounded operator. Yeah. They're two independent operators. Okay, this structure may or may not be familiar to you. If you've done any thermal field theory, when you look at two-point functions, this is exactly the structure that you find. Okay, so this is somehow related to thermal field theory, or just thermal quantum mechanics even. Doesn't have to be field theory. And in particular, if it's natural to look at this structure and sort of just extend this to a periodic function, just over the full S plane. And this periodicity is somehow related to the thermal periodicity that you're used to. Okay. But when we do that, when we extend it to this periodic function, then now we're going to get sort of discontinuities across branch cuts. And it's natural to ask about what their meaning is. Okay. So so to examine it, let's set S to be 2 pi I times a parameter x, and so this is sort of the imaginary part, and x is going to go from 0 to 1. And let's just compute what this function is. This function is if it was a tensor product. So if in that case, these are operators, all in the region A, so I can just reproduce, I can replace this expectation value by a trace of the reduced density matrix for that state. And I can replace the modular flow by the action of the reduced density for that state. And what you find is that f of s with these values takes the following. Looks like this. A twiddle. X. T. So this is the real modular flow, and this is the imaginary modular flow. And then notice that if I set x to 1, I get rho here, And if I set x to 1 here, this guy cancels with this using cyclicity of the trace. Okay, so if I use cyclicity, then when x is 1, so f of 2 pi I plus t is just then, well, using cyclicity, now I have this guy first, OAT, and now I have OA twiddle over here. And so, if I set x to 0, then the difference between these two is clearly just a commutator. Okay? So that means that the discontinuity across this branch cut, if I have extended this into this periodic function, is just the commutator of these two operators. So f of t plus 2 pi I minus f of t is trace of rho A, commutator twiddle. And this is one way of writing the KMS conditions, which expresses the fact that correlation functions are periodic in Euclidean time, or are almost periodic in Euclidean time, up to commutators. Okay, so this is thermal two-point function, where the fact that it's a thermal two-point function is obvious if I just replace the reduced density matrix with the Gibbs ensemble. Okay, and then modular evolution in that case is just time evolution. Okay. Okay, there's sort of more, there's other ways to write this KMS condition, which I'll write down so that you are familiar with them if you ever see them. There's a more sort of abstract quantum field theory way to write it. So we can write it in terms of just the correlation function to begin with, without making it a trace. And it's just a statement that if I shift the modular flow by 2 pi I, then I just get the object with the other ordering. You can write it, or you can write it like this. This is if you want to be really cool. So 2 pi I modular flow is just this delta operator. And I can set s to 0 because in any case modular flow, where s is real, sends you from an operator in the algebra to another operator in the algebra. So this is the KMS condition. Okay. All right. So I think it's somewhat useful at this point to give an example. So the example I'm going to give is just if you look at a conformal field theory correlator. So I'm assuming that it's a CFT. We're looking at a CFT, and we just write it out in Rindler coordinates. The reason for using a CFT is because I can write down what the two-point function of a CFT is. So example. So a CFT correlator in Rindler coordinates. So I mean, if I pick, here's my Rindler wedge, and if I have R is somehow this direction, like this, and then eta is this direction, or writing it out explicitly, something like this, and then the y coordinates just factor out. And then you can write the two-point function, a CFT two-point function, which is just the distance between the 2 points to some power, and that power is determined by the dimension of the operator. So you you can write it like this. And then you can write the two-point function, a CFT two-point function, which is just the distance between the 2 points to some power, and that power is determined by the dimension of the operator. So you write it as, you can write it like this. So you write it as, you can write it like this. And then you can write it like this. and then again the y coordinates just factor out, and minus 2 times the dimension of the operator, which I'll call little delta. So big delta is taken. Okay. And so, modular flow in this case is a boost. So if I shift one of the eta coordinates, it acts as a boost. And because this is a cosh, it's quite clearly, it looks quite clearly that this is periodic in Euclidean boost, which is then just a rotation. Except it's not really periodic because of the branch cut that exists in, there's a branch point when this function vanishes. And actually the structure in the eta plane, eta 1 minus eta 2, is exactly this, okay? And in particular, these are the branch points. There's 4 of them. This is, at least in the local case, you always find this gap where there's a branch cut and there's a gap here. But in the non-local case, in the generic case of modular flow, there'll just be some branch cut to the origin here. What is this gap here? Well, we can draw a picture of what modular flow is doing in Rindler space. It's quite simple. Here's Rindler space. Let's say I have 2 operators, 1 and 2. These are the 2 operators, the 2 locations of the operators here. And then I'm flowing 2. So 2 is being boosted up and down like this. And so this is sort of, if I started here, this is sort of S is 0. And then I'm moving backwards and forwards in real time, in real boost parameter. And what are the branch cuts? Well, they're exactly where you cross the light cone singularity, the light cone of operator O1. Okay, so it's when the 2 operators become they become time-like separated from being space-like separated. And of course, the commutator that we just wrote down with the KMS conditions is just the commutator of these 2 operators, O1, O2. But this is 0 as long as they're space-like separated. So that's why there's a gap here. There's no discontinuity across the branch cut. Okay. Are there any questions about this? Okay. All right, good. That's probably familiar to everyone. Okay, but one thing I should say is just to have some intuition, and this intuition may or may not be actually justified, although I think I know how to justify it. That's the intuition that if I have sort of generic modular flow with respect to some other state, maybe not the vacuum, or maybe I don't pick the Rindler cut, I have some crazy cut, my region is crazy. But as long as I go close to the boundary of that region, so close to the boundary of the region, locally it kind of looks like Rindler space, the intuition is that locally the modular flow operation, okay, should act like a boost there. Okay. Yes. Yes. That's what I mean. Yeah. Well, I told you the condition. So Nima is asking about what states I'm using when I define modular flow in the non-local case, and I'm always using ones that satisfy the conditions, which is cyclic and separating, and those are finite energy excitations of the vacuum. You can show that at least. I mean, yeah.
That's a generic property.
It's a generic property. Yeah. The cases where it's not true. You can imagine, for example, if I took Rindler space and I just wrote the state as some factorized state. Okay. That's obviously not true. There's no entanglement, but that's also very singular. Right, so it has infinite energy. Yeah. So yeah.
Or you could just act with a projection on
Yes, Aaron keeps bringing up the projection offers. Yeah. Okay, good. Yeah, so this is kind of some lore. Even the non-local case, modular flow looks like a boost for acting on operators close to the boundary of A. Okay, so that's just some intuition. Boosts will somehow play a role. Okay. All right. So now, maybe I should motivate this a little bit better than I have. I should tell you why I'm telling you about modular flow and why I think it's cool. Yeah. Why is that? Yes. Well, that's the case where we know what the J operator is. We may not know what it is. Well, it's sort of by definition. This strip is analytic. You can show that. I mean, I didn't show it properly, but you can show it using the cyclic and separating property. Yeah, well, that's the point, right? Yeah, that's right. That's right. That's the KMS condition. That's the thing that I just did, right? That guarantees you always have some kind of periodicity. And I should have said, yeah, this is for any state. So this is not any state, but this is for these special states, which are generic. And this is some kind of thermality for generic states, even for non-equilibrium situations. So, yeah, that's right. That's right. Yeah. Yes. Yes.
And then did you also say that all of the finite energy excitations of like in a CFT or generically you said were separating?
Yeah, I said they're both cyclic and separating. Yes. So
If you took like the ground state and acted with a local operator, and that local operator squared to 0.
that's not possible, I don't think.
Okay, so that's what
Mm-hmm.
there are no local operators that square to 0.
For example, yeah. Okay. All right. So why modular flow? Yes. Good question. I suspect the dimensionless parameter is like the extrinsic curvature. For example, so Nim was asking what it really means to be close, and I'm not totally sure because this is some intuition that hasn't really been shown. But I think it's roughly that if you have some extrinsic curvatures, then you're much closer than that the scale set by that if the surface is curved. Yeah, and then there's also scales in the state, and they would have to be small with respect to that as well. Well, I think you can justify this using these methods that I probably won't get time to talk about, but using this defect OPE method. So if I think of, in the replica trick, if I think of this defect as a non-local operator, then you can talk about local operators on that, and that at least gives you some handle on modular flow. Yeah. Okay. All right. So why modular flow? Well, some of the motivation is, as I've said, it's an important and robust consequence of entanglement. And the other thing that we're interested in this conference is that entanglement is somehow the key to emergence of the bulk in ADS CFT and likely in quantum gravity in general. So it's no surprise that there have been recent applications of modular flow exactly to this problem of bulk reconstruction. So let me just list stuff before I give an example. this paper by Jaferes, Lufkowicz, Moldesina, and Su was sort of one starting point for this, where they noted that there's an important relation in ADS-CFT, which is that bulk modular flow is equal to boundary modular flow. So this is a way to map things in the bulk to the boundary using modular flow. With Aitor, Lefkowicz, we explored sort of the consequences of this, the implications for this program of bulk reconstruction, which you've been hearing about from Xi. There was some interesting papers by a lot of authors, some of which are here. Salton, Kotler, Swingle, Walter, Hayden noted that there's a explicit recovery map that does bulk reconstruction. If you look at that recovery map, it has modular flow in it. More recently, we worked on a proof of the quantum null energy condition, which heavily used modular flow, and it used modular flow for these non-trivial states. And so basically, this program was inspired by some constraints on bulk reconstruction, which related to sort of bulk causality and how it relates to boundary causality. This thing called entanglement wedge nesting, which maybe I'll mention. But that statement seems to map under this proof to analyticity in the S-plane. So this analyticity is somehow related to this, to bulk causality. So I think there's sort of these interesting connections. And so let me just go through a few examples, okay? Are there any questions? All right. Okay, so let me give some applications. The first one application. Okay, the first one is the following observation. So let's consider the following operation. Let's say we have an operator and we flow it by some real amount, S, and then we integrate over all of that flow. And let me just assume that such an integral exists, and we'll explore the consequences. So with Aitor, we called this a zero mode, because this is like taking a Fourier transform where you've set the frequency to 0. So in particular, this operator commutes with the modular Hamiltonian. Okay. So an interesting consequence of actually the KMS conditions, and that's why I sort of went through them in some detail, is that if you stick this object into a correlation function with another operator in the same algebra and compute the commutator in the state, so we evaluate the commutator in the state, 0. Well, what do? We write this integral minus infinity to infinity. We have two terms. Let me write the second term first. Psi O twiddle modular flow O just O, no twiddle away. Psi. So these are two different operators. This is one operator, and twiddle is another operator. But the next term is the opposite of this, and so we can use the KMS conditions to reorder it again. And so the next term after application of the KMS conditions is just, so this is at x, twiddle, what am I saying? I'm sorry. I was not watching my notes. Okay, sorry, let me just start again. So I can write this as the commutator of OA twiddle with modular flow acting by an amount minus s. So the modular flow is in here, but I can easily pass it to this guy just by boosting in the other direction. Psi. And now I can use the KMS conditions on this. There's two terms. First one, which is just OA of x, OA twiddle of minus s, psi. And then the next one looks like this. OA, where it's a commutator, but then I use the KMS conditions to reorder it. And then I have to include a shift of 2 pi I. Okay. And so what is this? Well, it's an integral over S, but along two different contours in this plane, right? So I can go up to this plane. The first contour is along here, and then the second contour is along here. So if I make some assumption about, the modular flow at large S, I can complete the contour and I get 0. Okay. So that means that at least acting within states, this commutes with operators in A. Okay. Good. But it also commutes with operators in the commutant because it's made out of stuff which is only in A. Okay. So it sort of commutes with everything, although it only commutes in the state. So we have to add a little bit more structure to this discussion. Let's assume that we're in a free theory. So we're going to assume that we have a free theory. In free theory, and the state that we're using for modular flow is Gaussian. And so what do I mean by that? I mean that all correlation functions, and so when I refer to a free quantum field theory, I usually use the field phi instead of O. Then all correlation functions are determined by sort of Wick contractions, right? So so which means that they're determined by the 2-point function. So if you know the 2-point function, and that's sort of what it means to be Gaussian, then you know all of the correlators. In particular, if you ever have a commutator in any of these things, if you do a Wick contraction that comes out of the commutator, you're just going to get 0. So that means that you can always replace commutators with their expectation value, say times the unit operator. And so everything is sort of determined by this. And so that means that now I can just use this as a statement outside of the state. And so that means in this case, for free quantum field theory, these zero modes, these modular zero modes, are these modular zero modes do actually commute with all the operators in A, and they commute with all the operators in the commutant. So in some sense, they're in the center. Okay. Sorry, this is sort of question mark. There's a subtlety. There's a subtlety in that they can't really be in the center, because if I take correlation functions of them, two of them, take two different modular zero modes, then actually you find that these S integrals just diverge. And so they're not bounded operators anymore. But that's a detail, so I think this is still an interesting observation, and you can still certainly insert these things into correlation functions and get answers for those correlation functions. All right, so the commute, sorry, which is this, I don't think I really defined the center, which is to say that they commute with the operators in the algebra of A and in the commutant. Okay, so let's explicitly try to calculate these zero modes. And there's sort of a trick that we can use to calculate them. And the idea is very simple. So we have sort of, these are meant to be defined for general modular flow, non-local case, but let's just look at the local case for simplicity. But this does apply to the non-local case as well, actually, which may be a little surprising, but we worked it out. And so we have this operator, let's say it starts here at some point x, and then we can module a flow, which in the local case is just a boost. In the non-local case, it's just this operator becomes some non-local operator that's sort of spread out over the domain of dependence of A. So, but it always sort of stays in the domain of dependence of A. And let me take a slice, a Cauchy slice, that goes through the boundary of A here. So this is the boundary of A. And let me do some manipulations where I take this field, which is flowed by some amount, say phi of S up here, and let me just sort of rewrite it as an operator on this slice, sigma. Okay? So I can always do that. I can just use the equations of motion. This is a free field. Let's assume it's a free scalar Klein-Gordon field. I can just solve the wave equation, and then I can just write it as an operator here. One way to do that explicitly is just to assume that phi of S can be expanded in terms of the field operators on sigma. So this is an integral over y, which is on sigma. And this is a bit schematic. But you can also have the conjugate momenta. And then you can compute these guys. You can compute what g phi and g pi is just by calculating commutators, by using the canonical commutation relations for the fields on this Cauchy slice. So they look something like this. Probably should use y here. Okay, so you can just you can see that if I take this equation with the g's unknown, then I can just take commutators of both sides of this equation. I get a delta function, so I just pick out various things. Okay. Okay, so you do that, and so for example, Eg, you find g pi s of y is just minus I, the commutator phi of s with phi of y. Is that what I want? Sure. For example, but now let's just integrate over s, because we have to do that to define the zero mode, g pi s. But this is a commutator, and so we can just use this analysis to show that this is zero. Okay. So that means that all of these g's are zero. And so that means you seem to have a tautology. This zero mode should be zero. You have to do the analysis much, much more carefully when you think about operators on the slice as a function of y that come close to the boundary of y. If you do it much more carefully, and I'm not going to go into details, you actually do find a contribution from operators that live exactly here. So this is the intuition that the zero modes are really operators that live here. Okay, so what do you find? You find that, okay, let me write it out explicitly. The zero mode, which is an integral, modular flow, can actually be rewritten as an integral over the boundary. So all operators on the boundary of the region A contribute, times the field operator at that point, and a two-point function between the field operator and that point and the field operator of where you want the zero mode. Okay? So, okay. So i.e. zero mode on the entangling surface, which is just the boundary of A. Now, good. Now, one thing to say is, again, you find, before I told you, if you sort of can study correlation functions of two of these zero modes, you find infinities. So it's not really a well-defined operator. Actually, on this side, you find the same thing, but for a different reason. If I study correlation functions of two of these, then these two of the operators come close, but they're coming close on a codimension 2 surface. And as I told you in the beginning of the class, that you know, to talk about quantum fields, you need to smear them, and you really need to smear them over this codimension 0 surface. So you always find divergences. And so those divergences match somehow. Let me emphasize, this is true in the non-local case, with the condition that my modular Hamiltonian is somehow Gaussian. And so that really means that the state is Gaussian. State. All right, so it's determined by Wick contractions. Okay. Okay, so this is interesting. This was a free theory, but another situation where correlation functions factorized like this is just generalized free fields. Okay, and so generalized free fields are somehow fields determined by their two-point function, but now the two-point function doesn't have to be that of, the two-point function of a Klein-Gordon field. For example, in CFTs, we might be interested in generalized free fields, where you just take the two-point function to be that of two-point function of some operator with some dimension. Okay, and these are relevant in ADS CFT because these generalized free fields is how we sort of interpret the fact that the bulk theory can be free. Okay, so there's some map between the bulk theory and the boundary theory, and in some situations you have free quantum fields in the bulk in some limit, and that maps to the fact that correlation functions in the boundary CFT look like generalized free field correlation functions, and they factorize like this. So now we can apply this whole machinery to that situation, and what we find, instead of the zero modes being localized on the entangling the boundary of the region A, they get localized on the root Takenagi surface. Okay. However, to prove this, we need to add one thing, which is this JLMS result. Okay, so functions also factorize for generalized free fields. So now, and the context for this is often, well, not always, but ADS CFT. And then we can use this JLMS result that tells us that bulk flow is boundary flow. So I'll explain that now. So the idea is that, so the idea is, I'll just draw in pictures, and I think you've seen some related pictures by Xi. We have some CFT that lives on the boundary. We have some holographic Z direction. I'll just draw it in Poincare ADS. And then we have some entangling surface associated to some boundary region A. And the entangling surface is associated to some bulk region little a. And you have some quantum fields here in the bulk, which are, let's take to be free. And that maps to some operator O, which looks like a generalized free field. The leading order in 1 over n, where n is some, is some parameter in the bulk, which is like 1 over g Newton. And so we're taking g Newton to 0. And the standard dictionary in this situation, there's some correspondence between the field and the bulk field and the boundary operator. In particular, there's this extrapolate dictionary, which tells you that they are precisely related near the boundary up to some factor. And so now the statement of JLMS is that the bulk quantum fields that you can associate the region A to some reduction of the fields in the bulk to the region A. You have some modular Hamiltonian associated to that region, and the full modular Hamiltonian maps to the full modular Hamiltonian of the boundary region, and this is the JLMS result. This is the RT surface. Okay. And now, so if we apply, so if that's true, then modular flow should also map. And so we apply modular flow to the extrapolate dictionary. This should be true. Yes. Yes. I put hats here. They're the full, it's the full modular Hamiltonian, yeah. That's, yeah, the area operator cancels. Yeah. Oh yeah, oh certainly. But I think that's all I'm using here. So, yeah. I'm probably using a little bit more because I'm assuming modular flow maps, which may not directly follow from what they said, but we think it's true. Okay, so we think this should be true, and so that allows us to, it allows us to apply this zero mode formula to CFT correlation functions for operators just by using the extrapolate dictionary to push them into the bulk. And so that means you can write a formula now. Okay, so apply to the zero mode. So you can write a formula which is meant to be true, at least the leading order for generalized free fields. If I have some region for some point in the domain of dependence of A, so that's on the boundary, say here, and I compute the zero mode, I integrate over all of modular flow like this, then I can relate that. I don't know if there's a 4 pi, I don't know if I included that. There's a 4 pi integral now over the RT surface, because the bulk is a free quantum field theory, and so I'm applying the zero mode formula really in the bulk, and I'm assuming the state in the bulk is Gaussian, so I can apply that, and then I get the operator on the RT surface, and then the correlator. Well, it's now a bulk to boundary correlator between the bulk fields and the operator on the boundary at this point x. So you get an integral over operators on the RT surface, so fields on the RT surface, multiplied times the correlator between these 2 points. Okay. This formula here, sorry, which formula? Yeah. Yeah, no, that was assuming. Sorry, this was a general discussion. Now, and then I talked about free quantum field theory on the boundary, and it's true. Then it gets pushed to the entangling surface. But now, in the situation of generalized free fields, we should interpret it in the bulk, because in the bulk, then I really have a free quantum field theory, and then it gets pushed to the RT surface. Right. So. And the interesting thing about that is that now we can reconstruct operators, in principle, using this equation on the RT surface, and that's in this entanglement wedge, which in some situations is highly non-trivial to get to. And of course, the non-triviality we've mapped to the statement about modular flow. Okay. So yeah, let me box this equation, because I quite like this formula. There's some relation here to the story of OPE blocks that you might be familiar with. In particular, if I take, this is true for a non-local modular Hamiltonians, but if I took this to be a local modular Hamiltonian, and I integrate the right-hand side over the slice A, then I get a formula which is called the OPE block, which is a relation between the integral of the field of the RT surface in the local case and the integral of the operator in the boundary causal domain D of A. Yeah. Oh, nothing. Sorry. Yeah, nothing. They're the same. Good. Yes.
In the general case, do you expect that the zero modes have support near the boundary?
In the general case? Yeah, I'm not sure. So yeah, it's interesting. It's only true as a statement about correlators in the general case. So yeah, I'm not sure how to think of these in the interacting theory, and I think that's really an interesting question to ask.
There is something to say about the non-zero modes.
The non-zero modes?
Yes.
If I Fourier transform this? Yeah. So we discussed that in this paper with Aitor. And you can try to reconstruct them as well. The formulas are much more complicated. Yeah. Sorry. Okay. All right. So are there any more questions about that? Totally going to run out. Yes.
So, I mean, it's tempting to try and interpret this as a sort of generalization of what happened in HKLL, where you sort of proceed by solving the bulk equations of motion using the ordinary.
Yeah. That's right. And that's how this works with the OPE block as well. This then just becomes the boost, and so that's sort of the ordinary Hamiltonian. That's right. Yeah. And I should also say, that there should be, there should be corrections because there's 1/n effects. I cannot literally localize this operator on the RT surface. So there's some issue there, and there's also the issue with the smearing, and these correlation functions will again diverge. But yeah, it's still yeah. Questions? Yeah.
So I understand what the modular flow is doing, technically in terms of how it's pushing the operators around. But is there a good physical intuition for what modular flow is actually doing in terms of? I mean, it just seems like kind of a trick. I mean, I just don't have any physical intuition for it.
Yeah, I sympathize. Yeah. Jordan is asking about the physical intuition of modular flow, and I don't have much of one, but I feel like ADS-CFT is sort of giving us one because it's mapping, this under this map you get to map the boundary modular flow into the bulk, and the bulk modular flow is complicated, but it's not that complicated because it's a free quantum field. So whenever you do modular flow on an operator in a free quantum field, it just rewrites it as some complicated superposition of different operators in the domain of dependence of that region. And now it's the domain of dependence in the bulk, but yeah. So it's, I think, yeah, we should get our intuition from ADS-CFT as usual. Yes?
So if you can't quite exactly localize it, probably I would guess that it's the straight scale that enters. You probably couldn't localize it
Yeah. Yeah. I'm not sure. Alex is asking about where the corrections with this would enter, whether they're Planck or stringy, I guess. The only thing I have to say is that this large S integral that I had to do is somehow related to the resolution that I get at the entangling surface. So there should be some relation between, I should really cut this integral off likely, and there's some relation between that cutoff and the cutoff in the bulk. And the large S in other contexts, there's interesting things that happen after late times, where time is of order, is of order 1/g Newton or something, and I'm not sure about stringy stuff, but yeah. Okay, more questions? Yes.
So presumably at the center of this is this twirling map, or this map for extracting the zero moment from an operator. And if you were to think of this as a map, because it's not a normalized map, and this is what you say is one of the origins of the divergence, could you say something about, let's say, if you have a normalized operator, say instead of a field, say some unitary operator, how this would change the norm?
Oh, I think, well, I'm doing this funny thing where I think of, I'm imagining I could smear this operator and make it bounded and so forth. And I think the issue is coming from the modular flow. It's not from that. Yeah. But yeah, I don't have a great answer. Sorry. We can talk about it after. Okay, let me move on. So this was one interesting application of modular flow, I think. And let me go to another application, which I was originally, I was going to focus on talking about perturbative approach, but I sort of got sidetracked, but let's come back to that. But when you start doing, it turns out when you start trying to do perturbation theory, for basically, for dealing with these things, these objects, entanglement entropy or whatever, in local quantum field theory, where I'm thinking about starting at a point where I have a good understanding. So that would be if I had local, the local case, right? So I know what the modular Hamiltonian is as an integral over the stress tensor. So there's some simplification there, and then I imagine sort of perturbing away from that situation. Then it turns out that the perturbation theory is controlled by this modular flow. And maybe that's not so surprising, but it comes up, and this was my introduction to modular flow at least, so I will go through it. Okay, so a local modular Hamiltonian is sort of very powerful. So it's it's a good, it's a powerful starting point for perturbations or something. So let's perturb around it, and the original idea for doing this was initiated by Vladimir Rosenhaus and Misha Smolkin. And so I'm going to discuss this a little. Okay, so what might we go after? Well, one thing you can go after is, one interesting thing to go after, and I think this was their motivation, is to imagine a CFT. And if we have a CFT, we know a case which is sort of seemingly a little bit non-trivial, where we have local modular flow, and that's where the A region is a ball, and the state is the vacuum. Then log sigma A now for the vacuum is local. Okay, so but then maybe we want to understand what happens when we move away from a conformal field theory. So what's one thing we would do? We would add a relevant operator. So you have your CFT action, and then you add to it some relevant operator with some dimension delta, where delta is less than d. And then you might try to use this to probe the renormalization group flow that you get after acting with this operator. And so, if this was some kind of a mass deformation or something like that. And this approach is sort of similar to how you would go about conformal perturbation theory. Okay. So what do you do? Well, actually, let me do a simpler thing. This is a little bit complicated. You have to integrate over the operator over all space. There's various infrared divergences. It's a little bit non-trivial. Let me do something related but simpler. So what we're going to consider is, well, we're going to go back to our sort of path integral picture, which allowed us to produce a path integral representation of the density matrix. Okay, so this is some path integral, Euclidean path integral. So this direction is Euclidean time. And if I just did it, a Euclidean path integral with no insertions for infinite time, then I would project onto the vacuum. But let's say I want to look at a different state, which is some excited state. One way to do that is just to turn on a coupling to some source, j of x. And so you would take the CFT action in the path integral, and you would change it by an integral over the rest of the dimensions times j and the operator insertion. Okay, and to make things nice and easy to deal with, we can just localize this deformation in some region here, and that'll just produce some excitation which has some finite energy and so forth. Okay. So one thing you can do is you can sort of rewrite the Euclidean path integral as some time-ordered exponential, including this deformation, acting on the vacuum. And of course, the time ordering just comes because we're doing a path integral, and these operators don't necessarily commute at different points. And then what we're going to do is we're going to take this and expand in J. And then we want to do perturbation theory, and we want to compute quantum information objects. We want to compute entanglement entropy, whatever you want. But the important thing that I would like to emphasize is what you get is modular flow. Okay, again. Okay. So this was the state J, but let's say we wanted to produce the density matrix, the reduced density matrix. Then we have to do this double path integral, one from tau plus infinity, tau is minus infinity. Okay, so you get some picture where we have our A region, and then we have sort of two boundary conditions on the top and the bottom of the A region, and we're freely integrating over here. We have our source, J, but then we also have our conjugate source here, which is producing the other state, the ket, or the bra, in this density matrix. And it has to be reflection of this, because it's the Hermitian conjugate, and when you Hermitian conjugate in Euclidean time, you reflect. Okay, about this axis. So the Hermitian conjugate, J. And so then, in the usual thing, now we reinterpret the path integral, which we were interpreting like this, as an angular path integral. And so we can write an expression for this density matrix, which I'll call rho A, as, again, well, it sort of looks a little bit like this, where we have something acting on the vacuum, but now it's something acting on the density matrix. And the something is some angular time ordered. So this is the angular direction theta. So you have to time order things in the angular direction times the source. And now in the source we have to include both J and its reflection. So really J hat is J plus J dagger. And so this is sort of a very, very formal expression for the reduced density matrix. But we can expand, and you have to normalize it too, but I'm not going to go through those details. So, and so you can expand in J, and at first you get the density matrix for the vacuum, reduced density matrix, and then you get some corrections, and then so forth. So something at order J, something at order J squared, so forth. Yes? It is if this is true. This reflection symmetry guarantees that. It's not totally obvious to see, but yeah, you have to rearrange this time ordering and various things. Yeah. Yes? Oh yeah, so this is the vacuum, this is the density matrix. If you can make sense of that for the vacuum. Right, so if I had no sources, this would just be the angle. This is just the usual trick. Okay, good. Okay, so now we're going to compute information theoretic quantities with this density matrix. But one issue that arises at some order is you have to deal with the fact that these two matrices don't commute, and so when you're expanding various things, you have to deal with that. So, so for example, e.g., you might want to compute the entanglement entropy. And so if we expand the entanglement entropy, then at first order, okay, so we have to expand this log. So I told you, if I take a log of the sum of two density matrices and they don't commute, then you have to be a little bit careful. But at first order, you don't really have to be careful because of the trace. So the trace here, so you can use cyclicity of the trace to write anything that you find when you do the expansion as the change times some function of the undeformed thing. So at first order, I can expand these matrices as if they were C numbers. So, so ignore commutators. And then the first order contribution to the entanglement entropy, well, you get two terms, one from where you deform this guy and one from where you deform this guy. So the first one is minus trace delta rho log rho A, or sorry, sigma A, minus trace sigma A delta rho A sigma A inverse, because then I'm just expanding the log, and if I assume that was a normal number, then I can just do this. But then cyclicity, I cancel this, and then this is 0 because I'm assuming that my density matrix is normalized, and my previous density matrix and my new density matrix is normalized. So you have to deal with normalization and so forth. But let's ignore that and assume that it's not normalized. Then it's true that you get this expression. So this is the only thing, and so you can write this as 2 pi times the change in the expectation value of the modular Hamiltonian for the vacuum. So Ka vacuum modular Hamiltonian. And this is what's known as the first law. First law of entanglement, thermodynamics, or something like that. And that's just because it's relating a change, so this is really the change in the entropy. That's what I mean by order 1. At first order to a change in the modular energy, and so this looks like a first law, where the temperature is really 1 over 2 pi here. Okay. And so this thing has been quite instrumental in various people's exploration of entanglement entropy and holography. You can get Einstein's equations from this. This somehow maps Einstein's equations in various situations. The derivation of JLMS comes from this, and so forth. But I'd like to go beyond this and go to the next order. Okay. Yes. So I'd like to go beyond this. I think I want to keep this. I'd like to go beyond this and go to second order. And so it's second order, you do have to deal with the fact that these different matrices don't commute. And one way to deal with that, okay, so second order. Okay, delta rho. So one way to deal with that is to especially when you're computing entanglement entropy, you can give an expression for the log of a matrix as an integral like this. You can just check that this gives you the log. But this guy is much easier to expand perturbatively. Okay. This is just a trick, but it's useful to know. So in particular, you can do something like this. 1 over beta plus sigma A plus delta rho A, which is what you want. You can rewrite it as 1 over, you can essentially factor out this guy, delta rho A, and then it comes out over here because you're inverting, so you've switched the order. So this is just an identity, but now this is 1 plus a matrix, so you can just expand that. Okay, expand. Okay, so then you get an expression for the second order change in the entanglement entropy, trace rho A, log rho A, which is an integral over this beta times 2 insertions of the change in the density matrix with these sort of things here. And then you also get a contribution from the first law at second order. So this is just the change in the modular energy expanded to second order. Okay. So this is, so this is an important term, but this is kind of, in some sense, the more interesting term. But it's also important that it splits into these two terms, and so that's sort of we'll see that when we try to map this to holography. But okay, so there's some manipulations you can do here, but the first thing to note is that, roughly speaking, I can write to first order delta rho A times the inverse, and this is all very formal, as some integral over this source times the operator insertion. So if I just expand the time ordering to first order, I can ignore the time ordering, and then I just get the operator insertion. And so this, I have 2 operator insertions, and then I have some complicated functions of the density matrices. But maybe it's not so surprising, but I'm not going to go through it. You can rewrite this as a 2-point function of these 2 operators with modular flow. Okay, so the modular flow is dealing with sort of a way of rewriting this beta integral in time instead of, this is more like in energy. Okay. so let me just write an expression, because I like this expression and I use it a lot, and so I'm going to subject you to it, so apologize. It's quite an ugly thing. So this piece you can sort of think of, this is the modular energy, and remember the relative entropy is the change in the entanglement, is the change in the modular energy minus the change in the entanglement entropy. So this is sort of the second order term in the relative entropy. Okay, so let me just call it that. Second order term, relative entropy. And you can write it as an integral over the two sources, some factors, I won't care, as an integral over modular flow, I epsilon minus infinity, I epsilon plus infinity, times some kernel, which happens to be this sinc function squared, times the modular flow correlator. Now, I'm actually even this is complicated, but I'm even suppressing some details. There's some convergence issues that you have to deal with by picking various orderings and related to this I epsilon, but I'm not going to go into that. The important thing I want to focus on is the fact that this is some integral over modular flow. It's not the same integral, it's not this zero mode integral, there's this kernel in front. Okay. Now, in lieu of time, well, okay, so I wasn't really planning to do this, but you can do basically exactly the same analysis that I did for the free fields when we were analyzing the zero mode. And in particular, it's sort of the same analysis for the generalized free fields, where you sort of think of this operator as an operator, you evolve this operator, you rewrite this operator as an integral over operators on some other Cauchy slice, and you figure out what those kernels are. And then you can just do the modular integrals when you do that. Now, I'm going to do it in the bulk, so this is for generalized free fields. So the same manipulations as for the zero mode. What do you find? Well, you find the following expression. It's 2 pi, there are many things I have to define here, but it's an integral over A region, the bulk stress tensor in the presence of the source, the bulk killing vector, and then this normal element. So what does this look like? This is basically the expression for the modular energy, but in the bulk. And so what I mean by the bulk, I mean exactly the same picture as I drew for the zero mode and I erased. So let me add it real quick. So the picture, let me draw it really quickly again. A complement, RT surface falling down. Yeah, I guess I'm drawing a different picture here. This is the one where I have Rindler space on the boundary, and then I move that into the bulk in the Poincare direction, in the Z direction here. On the boundary, I have some causal wedge, and I have modular flow on the boundary, but it trivially maps to some modular flow in the bulk, which exists at fixed Z, acts at fixed Z. And this is the JLMS statement, but in the local case, which is kind of trivial. So there's some vector associated to this, and there's some killing vector associated to this, and this region here is A. Okay, so I managed to rewrite this second term in generalized free fields as an integral over this region. Good. So where T mu nu in the bulk is just the standard form for the stress tensor of a Klein-Gordon field, evaluated in the state J, where I take the source and I propagate them into the bulk. Okay. Okay. So the final expression is that the change in the entanglement entropy at second order has 2 terms. It's the second order contribution to the modular energy minus the second order contribution to the bulk modular energy. Okay. And so this is actually, in disguise, the JLMS relation, the more fine-grained version of the JLMS, which includes the area term. However, to make that connection, let me be real quick. Let me, what am I going to say? This guy, yeah, so let me write the relation between the change in the entropy and the change in the relative entropy. And so this guy is just the change in the relative entropy, as I said before. But the JLMS relation tells us that this should be the change in the relative entropy in the bulk for the region A. And so, good. Right, sorry. Plus the entanglement entropy, plus the entanglement entropy for the bulk fields. But it turns out the important point here is that the entanglement entropy for the bulk fields, it vanishes. And the reason it vanishes is because this source is producing a coherent state in the bulk, and the entanglement entropy for coherent states in free field theories, where you can define them, vanishes. Okay, so so the conclusion is that this term vanishes. Bulk entanglement entropy vanishes, and that's the bulk entanglement entropy of fields in this region with respect to this region. So maybe this is not so surprising. This is sort of the expected result. You could have derived this from the beginning. One interesting thing of note is that this two-point function is the two-point function of a CFT. It could be a two-point function of a CFT, which is somehow fixed and universal. And this formula still applies in that situation. So even if you have a theory which doesn't have a holographic dual, you can calculate entanglement entropy with some fake bulk, at least to this order. Okay, and let me finish there, because I'm way over time.